Welcome to Math 2320, Section 4.5. This is a fairly easy section and won't take too long for you. In this case, we'd like to take our differential equation and write it as a linear differential operator. So all this means is you look at your left-hand side here, our second order constant coefficient equation, and you could think of this as 4m squared minus 16, which is factorable into 2m minus 4 into m plus 4. And so if you think of this as your differential operator being factored, here is our operator L in this form that's factored. Well, similarly in question 2, it's a third order problem, but works exactly the same way. So first let's look at the polynomial m cubed plus 4m squared plus 4m. Factor out the common m. This part is factorable further as m plus 2, m plus 2, so a repeated root, or m times m plus 2 quantity squared. And that's how our differential operator looks like. In question 3 and 4, we look at something about a differential operator that annihilates. So what that means is, what does it look like that if I took derivatives, how high would I need to go to make all the terms vanish? So if this is f of x, what's f prime? Just a first derivative. Second derivative minus 24x. Third derivative is minus 24. But if I go one more derivative, the derivative of a constant is 0. And so the differential operator that would annihilate this function has to be d to the fourth power, which in essence means the fourth derivative. Well, what about here? What would d6 do? Well, d6, that means it's going to annihilate powers of x0, x1, x2, x3, x4, and x5. So one less than the power on your differential operator. So d cubed would annihilate 1x x squared. d7 would annihilate 1 all the way up to x to the 6th power. So again, it's the number of derivatives you would need to make all the terms go away. And in our last problem here, we have our second order constant coefficient non-homogeneous problem with initial conditions. They'd like us to solve this. Alright, so we first solve the homogeneous problem. M squared minus 36 is 0. That is factorable. I see that I get two roots. They are distinct. Alright, so we get our homogeneous problem. Based on the right hand side being 8, my guess from the method of undetermined coefficients is my particular solution is A. First and second derivatives are 0. And when I plug this into my problem, I see that A is a negative 2/9. So here's my general solution, but it must solve these two initial conditions. So plug in 0 for x, e to the 0 is 1. And so on the first case, I get C1 plus C2 is 11 ninths. I calculate the first derivative of my general solution. Plug in 0. According to the initial condition, y prime at 0 is supposed to be 0. And so I get minus 6 C1 plus C2 is 0. So I have a system now of two equations and two unknowns. I'm just going to multiply the first one through by 6 and then add them up. And so when I do that and I add them up, the C1 constants go away. I get 12C2 is 66 over 9, and multiplying by 1/12, I get C2 is 11/18. But from the first equation, I get C1 now is 11 ninths minus C2. So 11 ninths minus C2, convert the 11 ninths to 22/18 minus C2, and I get 11/18 for C1, giving us our full solution now, which matches the differential equation and both initial conditions.